Alright, so in this video what I'd like to talk about is how to determine the reaction order for several species and figure out the rate law from experimental data. Alright, let's look at this reaction for example. D plus E plus F goes to the product X2, whatever D, F and X2 may be. From what you've seen already, you can write out the basics of a rate law based on the starting materials that you have. And so what you can say is that the rate is equal to K, whatever that rate constant is, times the concentration of D, times the concentration of E, times the concentration of F. Now the one thing that we don't have on here that is particularly important is exactly how changing these concentrations affects the rate. Sometimes doubling the concentration here quadruples the rate. Sometimes doubling it doesn't do anything. That's what the order is for. The order gives a clear indication of how exactly changing the concentration of a species affects the rate. So what we need are three unknowns here. So we're just going to say X, Y, and Z. So that's the main issue right now. All we can do is say X, Y, and Z. We can't really say anything else. And we're going to use the experimental data to figure out what we need. And we're going to do each one separately. We're going to use a simple method to figure out X, Y, and then Z. All right, and so here's what we need to do. Let's figure out. We're going to look at D first. D, or the order for D, in this case X. All right. I want to see exactly what effect changing the concentration of D has on the reaction rate. And because all I'm looking at is D, I want to make sure that I do nothing to the concentrations of E and F. All right. So I have to find, out of these experiments, I have to find two experiments where the concentration of D changes, but the concentration of E and F does not change. And that actually happens to be these equations right here, equations 1 and 2, or experiments 1 and 2. D, the concentration of D decreases by a factor of 10 here. E doesn't change, F doesn't change. Notice that there is the initial rate information here as well. Now here's what we're going to do. We're essentially going to write out this equation twice on top of each other, but we're going to not include several pieces of information that we don't need to be concerned about. Because we're only concerned about the concentrations associated with D, and because E and F won't change, we can effectively forget that E and F are present for right now. And the same thing for K. We aren't bothered about K at the moment. We will be here in just a bit. So really the only pieces that we're interested in are the rate and the concentration of D. I'm just going to set them equal to each other and you'll see exactly why. One other thing, you always want to make sure that you put the highest rate on top, because you're going to be putting one rate over another, one concentration of D over another. You put the higher numbers on top because you've got this exponent here. Having whole numbers just makes the math easier to deal with if you have whole numbers rather than fractions. Now if you really like fractions, then fine, go ahead and do it the other way. But I always like to keep my high numbers on top, my low numbers on the bottom. Makes things easier to work with. Okay, so with that in mind, we're going to say, well, the concentration of D is highest in reaction 1, experiment 1. The rate's highest in experiment 1, so I'm going to say my rate is 5.00, this comes from experiment 1, times 10 to the 11. I'm going to set that equal to my rate, which in this case is 1 mole per litre per second. I'm not going to worry about units for right now. And then what we're going to do is we're going to put on the bottom the same thing, but for in this case reaction number 2. So I have my rate here, 4.99 times 10 to the 11. And then on the bottom I have 0.1. Now the only other thing we haven't taken into account yet is the fact there is this exponent X here that the concentration is raised to. So we're going to take our concentrations and raise them to that power. And what this is going to do is a way for us to calculate what x is. In fact, you can really get rid of one of these two equal signs. You can just put that equal there in the middle, just like so. Now you actually don't need a calculator for this, because you can see 5 and 4.99 are essentially the same number. They're both raised to the 11th power, so those divided by each other are essentially 1. And 1 divided by 0.1 is 10. Now you know the only way to get to the only value to have for x here, if this is going to be 1, is 0. X must be 0. Therefore, the order of the reaction with respect to D is 0. What does that mean? Well, that means if you increase the concentration of D, as you do from reaction 2 to reaction 1, notice the concentration of D increases by a factor of 10, which you would expect to give an increase in reaction rate, but it doesn't. Okay, so something that's 0 order, its concentration change will not affect the rate of the reaction. Now let's look at E. And we're going to do the same thing. We want to find two reactions where E changes, but F and D do not. So we've got 0.1, the only other one here is 0.2, and if you look at D and F for those two, they do not change. So therefore we're going to do here. And like I said before, let's see, we are going to put these concentrations here. We have to decide which concentration goes where. We're going to put our higher concentration on top. That corresponds to our higher rate as well. So if we just do that so we have reaction 4 on the top, 1.99 times 10 to the 12th, and the rate corresponding to that is 0.2 moles per liter per second. And then on the bottom is going to be the rate from equation 1, and then the concentration from equation 1. Again, we make those two concentrations with the exponent y. Now 1.99 times 10 to the 12 is approximately 2 times 10 to the 12 if you divide this out. This is 4 times as big as this. So therefore those two numbers give you 4 on the left. 0.2 divided by 0.1 of course is 2 to the power y. Therefore y must be equal to 2. Therefore the reaction is second order with respect to E. So what that means is if I double my concentration of E, then I quadruple my rate, which is exactly what happens between reactions 1 and 4. Alright, now we're going to look at F. We have to ask ourselves again, which reactions are we going to use? Alright, I'm just going to write out my already. So, F. F is right here. F changes between 1 and 3. So, between 1 and 3, F changes. And also between 1 and 3, D and E do not. Same thing again. Put the high concentration on top, the high rate on top. So for reaction number 3, we've got 9.89 times 10 to the 11th. And the initial rate of F that goes along with that, or the initial concentration, is 2 moles per liter per second. And then from reaction 1, we have 5.0 times 10 to the 11th. And then we have that equal to 1 mole per liter per second. 9.89 times 10 to the 11 is almost like saying 10 times 10 to the 11 or 1 times 10 to the 12. What that means is that when you divide these out, you get 2, because this is essentially twice as big as this. So 2 is equal to, now of course 2 divided by 1 is also 2. And so that 2 to the power of z, of course, z must be 1. Therefore, the reaction is first order with respect to F. So if you double the concentration of F, you should be expected to double the rate. So, we're almost done. All we've got to do now is just write out our rate again and put in our exponents. Alright? So we know that the rate of the reaction is equal to K times the concentration of D raised to the 0 power times the concentration of E raised to the 2nd power times the concentration of F raised to the 1st power. We don't need to show the 1 because the lack of a number implies 1. Now there is one other way to show this. Anything to the power 0, like we said before, is 1. So effectively we don't need that concentration value for D here. So we could also say the rate law for this reaction is as follows, and we completely get rid of D. Just like so. So what if a question asked you one more thing? What if the question said, well, can you figure out what the rate constant for that reaction is? Well, the answer would be, well, yes, I can, because I have 4 sets of data here, and I can use any one to figure out the rate constant. The rate constant should be the same each time, but all I do is, let's say I'm going to use the data from experiment number 1. I plug in my rate, I plug in my initial concentration of E, I plug in my initial concentration of F, rearrange the equation, get K by itself, and that would be my rate constant. Alright? Okay, anyway, I'm hoping this video has made things a little bit more understandable, how to determine reaction orders, because that is how you do it. Alright, thank you.